Welcome to the presentation on automatic differentiation in Clojure with SICMUtils. My name is Tovieye Ozi. I'm a software developer based in Lagos, Nigeria. My contact details are on screen. The GitHub link for the repo this presentation is based on is on the screen as well. This talk is based on the SICMUtils library, and this is the link to the GitHub repo for the SICMUtils library. The SICMUtils library itself is based on a SICM library called SICMUtils. SICMUtils was developed for the book Structure and Interpretation of Classical Mechanics by Gerald Sussman and Jack Wisdom. Many Clojurists are familiar with another of Gerald Sussman's works, Structure and Interpretation of Computer Programs, SICP. Also, there are many other resources I consulted in the process of making this video. There's an article on dual numbers and automatic differentiation by Sam Ritchie, and there are many other videos for the SICMUtils library. Have you seen a math equation that you wanted to explore? Where do you turn to? Python, Matlab? We can actually handle all of those problems right within Clojure. During the course of this presentation, we'll look at a small physics problem. What happens when you throw a ball straight up? And we'll answer a few questions like how high does the ball go? How fast is the ball traveling at any point in time? We will be using the following libraries in our exploration. The depths.eden is shown on the screen. We'll be aliasing the SICMUtils.env namespace as env, and we'll be referring several functions from that namespace. A quick search for the height of a projectile thrown up online gives us the equation shown on screen, where y is the height of the projectile, v0 is the initial velocity with which the projectile is thrown, t is time, and g is acceleration due gravity. We can write this equation out as a Clojure function, which is what you see on the lower left, the height function, which takes 3 arguments. You'll notice that the math operators have the env alias from SICMUtils. They are all from the SICMUtils.env namespace. The env namespace provides these versions of the Clojure core functions because these versions are genericized. That means that they can operate on more than numbers. For example, the minus operator can subtract symbols, matrices, and other data structures. We could write the same function using the Clojure core functions, as you can see on the right, but then they would not be able to support many of the SICMUtils capabilities. On the screen, you see my Clojure namespace rendered to a browser window by the Clerk library. Let's call our height function with time of 2, initial velocity of 20, and acceleration due gravity of 10. We get 20. If we call the height core function with the same arguments, we also get 20. Remember, the height core function uses the Clojure core versions of the math operators. We can also call our height function with Clojure symbols, and what we get is an expression in prefix notation showing the symbolic form of our equation, of our function. But we cannot call the height core function with Clojure symbols. We will get an exception if we do that. So how do we convert the prefix form of this expression to the usual infix notation that we're familiar with? We can use the simplify and to infix functions from the SICMUtils library to create a render function, and if we call our height function with that render function, we will get a text version of a symbolic version of our function in infix notation that we are familiar with. We can also render our function to LaTeX. We'll create a render Clerk version that renders the function in LaTeX, and this is what it looks like. We can rewrite our height function as height time, a function of one that takes one argument, time. We do this by substituting fixed values for the initial velocity and gravity. In this case, we'll take an arbitrary value of 40 for initial velocity and 9.81 for gravity. With our height time function in hand, we are now ready to plot a graph of height against time. First, we'll use a utility function to round all values to 2 decimal places. Then we'll get a set of time values, a series of time values starting at 0 and ending at 8.4 with an interval of 0.2. We'll map our height time function across those time values to give us height values, and then we will map against both time values and height values to create a series of Clojure hash maps with a height and time key. This series of values will go into a Vega plot created by Hanami, and finally we can call the Clerk Vega renderer on our height plot, and we get a graph. From this graph we can tell the approximate maximum height of our projectile, which is somewhere around 80, and the maximum height happens somewhere at the 4-second mark. Quick refresher on slopes and tangents. For a straight line, the slope can be calculated by picking any 2 points along the straight line, then dividing the vertical change between the 2 points by the horizontal change between the 2 points. The slope of a straight line is always constant, but for a curved line, the slope is always changing, and you can get the slope for any point on a curved line by calculating the slope of the tangent at that point. The tangent for a point on a curved line is a straight line that touches the curved line at only that point, at least for all points that are close by to that point. If you extend the tangent on a straight line, it may actually touch the curve at some point, some distance away from the tangent point. The slope is a measure of how fast y is changing with respect to x, or in the case of our height time function, how fast the height is changing with respect to time, the velocity of the ball. We can approximate the tangent to the curve at any point, to our height curve at any point, by picking a point very close to the point we're interested in and drawing a straight line between the two, and then we'll calculate the slope for that straight line. How fast is the ball traveling at time 2? Well, at time 2 the height is 60, and then we'll pick a second time which is close to the first. We'll pick 2.1. At 2.1 the height is 62, and then to calculate the slope we'll subtract the first height from the second and divide by the horizontal interval, which is 0.1, and that gives us a speed of 19.9 meters per second. That is the speed of the ball, how fast the ball is traveling. We can generalize this to a slope at function, which takes any function, a small delta, and the point at which we want the slope. So calling our slope at function on the height time with a delta of 0.05 and a time of 1, we get 30. At a time of 3, we get 10. At a time of 5, we get -9. That means the ball is, instead of traveling up, it is now falling. And at a time of 7, we have -28.7. The slope function tells us how quickly the height is changing for at a particular point in time. But this method has a shortcoming. It's an approximation. It is possible to draw a tangent line at any point for any point on our height curve. So just as our height is a continuous function of time, the slope is also a continuous function of time. So perhaps we could somehow transform our height function into a slope function, a function that takes only time and returns the value of the slope. One way to do that would be to modify our slope as function, and this is the result, an approximative function that gives us another function. The result of this function we can call on time, and it will give us a slope. But this function is also an approximation, so even if we get an approximate velocity out of this function, it will always be an approximation. Let's try the D operator from the SICMUtils library. The D operator is similar to the approximative function, but it is not an approximation. It is an exact transformation of the height function into a velocity function. And we can write a small function to compare all the three approaches we have looked at so far: the slope at method, our approximative function, and the D operator from SICMUtils. So we'll map over a series of time values and display the results in Clerk as a table. Looking over the results, we find that all methods are very close to each other, but the velocity obtained with the D operator is not an approximation, unlike the other results. So with this we come to an understanding of what the derivative is. The derivative of a function y is another function z that tells us how much the output of function y changes for small changes in the input to y. And the process of obtaining a derivative from a function is called differentiation. That is what the D operator is doing. It is transforming the height function into another function, velocity, and the velocity function tells us how much the height function is changing. We can call the D operator on velocity to get acceleration. Now that we have acceleration and velocity, let's expand our chart. So we'll generate velocity values from time values by mapping velocity against the time values, and we'll do the same for acceleration to get acceleration values. And we will want to make our chart a bit fancy, so we'll do things like add a line function to draw tangents, and finally generate plot data, a series of maps with keys for acceleration, height, time, and velocity. This is the Hanami template for plotting the height plot data. And finally we call the Clerk Vega Light renderer on our plot, on our Vega Light data, and this is what we get. We can see the height in blue. The blue line is the height, and then the purple line is velocity. The scale for the purple line is on the right. And finally below we have the green line, which is acceleration. It's flat and it's minus 9.81. We also notice that the velocity starts out at 40, and as the time increases the velocity drops until somewhere around the 4 mark. The velocity hits 0 and then becomes negative. So basically the ball thrown up, as the ball is thrown up, the velocity keeps on dropping, and at a certain point the ball stops rising up and starts falling back down to the ground. So our initial questions were, what is the maximum height of the ball? At what time does this maximum height happen? And how fast is the ball traveling at any point in time? We have answered how fast the ball is traveling because that is the derivative of the height function, velocity. What about the maximum height of the ball? One of the applications of differentiation is to find maxima and minima of functions. So at the maxima or minima of functions, the value of the derivative of that function is 0. That means the value of velocity will be 0 at the maximum height. We can call our velocity function with symbol t to view the symbolic representation of a function, and then we'll equate that representation to 0. So we can solve for t. T solves to 4.08, and so that means the time at the maximum height of the ball is 4.08. Also, the maximum height is the height at that time, which is 81.5 meters. There are a bunch of rules taught in introductory calculus for doing differentiation, such as the exponent rule, which says if you have a function of x to the power of r, the derivative is given by taking r to the other side of x, then subtracting 1 from r. And this is valid for any real number r. The D operator from SICMUtils is able to reproduce this rule and all the other rules from calculus. We can see this for a small set of functions by mapping the rendering of the original function and the derivative of that function using the D operator over this set of functions. And what we get in tabular form is this result. So for x squared, a D operator produces 2x, x cubed, 3x squared. And down here we have our height function and its derivative. The D operator uses forward mode automatic differentiation. This is different from other computational approaches to differentiation, such as numeric approximation. Numeric approximation is closer to what we were doing with the slope at function, or symbolic differentiation. Symbolic differentiation is like keeping all the rules for differentiation in your computer program. That is not what the D operator does. Rather, it represents every value in the expression to be differentiated as a dual. A dual is a value with two parts, the original value and the derivative is the second part. We attach a tag of epsilon to the derivative. And once this is done for all values in the expression, the D operator proceeds with normal simplification, adding all the terms, subtracting, multiplying, and if along the process a term comes up with a tag with a power of 2 or greater, that the value attached to that tag is discarded. A rough explanation for this is think of every tag as a very small number, and for increasing powers on a small numbers, we get more and more insignificant values. So we can discard higher powers of the epsilon tag without affecting the result, the accuracy of the final result. And this approach of forward mode automatic differentiation allows for obtaining the derivative of any program, because you can, provided the value in your program can be represented as a dual, you will be able to do differentiation on it. For example, if you can represent a closure feature as a dual, then the D operator will be able to obtain a derivative of the feature. Here's a breakdown of how the D operator would go about differentiating an expression such as this. First, every value would be represented as a dual. So we have the cos x squared term. That term is actually a composition of two functions, so the dual representation is not straightforward. So the derivative will be written as unknown at this stage, but there is a rule in the SICMUtils library that says that if you have a function and the argument to the function is itself a dual, then we can write out that function as the first part of the dual will be the function called on the argument without the dual representation, and the second part of the function dual representation will be the derivative of the function on the argument without the dual representation. So applying that to our cos x squared term, we can now write out the dual form of cos x squared as cos x squared plus epsilon 2x minus sine x squared. The dual representation, the derivatives for exponent terms like x and trigonometric terms like cos and sine are already inbuilt into the D operator. Then the next step is to carry out simplification, basically multiplying and adding all these terms together, and in the end we end up with a single dual, and you can see that the first term on the dual is the term we started out with, and the second term is our derivative, and that is what we're interested in, so we discard the rest and keep the derivative. During the course of this presentation, we have seen a good workflow for exploring physics problems in Clojure using the SICMUtils library and a few other Clojure libraries. We have also taken a surface look at the implementation of the D operator for automatic differentiation in SICMUtils. The SICMUtils library does a lot more than automatic differentiation. It has a large and growing list of operations that it supports, and you can see many of these at the link on your screen. That link takes you to a web page filled with worked examples of many physics problems. Thank you for listening.